Hello, I am Dongjin from LINE Media Platform team, and I'm in charge of development and operation. It's nice to meet everyone online. This is the agenda for today. And my topic today is LINE Media Storage at scale. First, introduction to the LINE Media Platform to help you understand better. And then this is the core part of the project, which is media storage forward placement, and the needs and challenges and the benefits of applying that. And lastly, after the release of the project, I want to talk about the future works. Media Platform is a core platform for LINE that supports more than 100 services, including messages, timeline, and albums. And it consists of OBS, Vision AI, and Live Function. OBS stands for Object Storage, and it operates distributed storage that enables secure storage of users' data. And OBS has a system, design, and infrastructure that enables LINE users to send and receive media from a closer location. I'll talk about this more in detail later. OBS also supports processing of user-saved original media. Images can generate various types of thumbnails, and videos can also be transcoded at a resolution desired by the service. In addition to this, the media platform is evolving into an ability to understand the media itself. It's Vision AI function that is responsible for that. It supports OCR, or adult image filters, to extract text from images, and functions to recognize and classify products. And also Live Function that supports the broadcasting environment required by the LINE service, from sending and watching live LINE broadcasting to chat and VOD are all included. And I'd like to talk about OBS, which is the foundation of the media platform. OBS handles more than 7 billion requests a day and accommodates more than 500 gigabps of traffic on a weekday peak time basis. And it has over 60 petabytes of secure storage. This is logical thinking that the physical scale that takes into account replicas and so on is larger than that. In the meantime, OBS has seen a steady increase in the traffic, and because of COVID-19, for the first half of this year, we have seen an increase in the total traffic. OBS has a significant increase in traffic when an issue occurs in a particular country, and also special days like Christmas and New Year's Day. And what you see here is a quote from this year's traffic response process. So the data is from Japan and Taiwan. And OBS is designed to deliver seamless service even in the event of a surge in such traffic. OBS accommodates the largest amount of traffic on a single platform by serving various media distributed online. And more than half of the line-wide traffic is handled by OBS. And the infrastructure, including the servers and network, are also configured on a large scale to handle this. And let's compare 2013 and now. The storage volume has grew more than 20 times, from 3 petabytes to 60 petabytes. And storage servers are now operating at more than 2,900, up from 270 in 2013. And 70 times increase of the user requests, and 3 times more of the requests. But the image processing has reduced. You can see that the OBS server has not increased in proportion to the size of the growth. So we needed to minimize the number of servers needed to operate by improving storage technologies, including storage capacity reduction technologies, and optimizing cache based on user media access patterns and activity utilizing GPUs. So let's take a look at the inside of the OBS. First of all, the user interface includes the OBS's service BO, which consists of components from authentication, storage, cache, and processor. Each component can scale out independently. Service BO delegates a series of tasks such as authentication, cache, storage, and conversion to each component while handling the business logic. OBS offers a variety of rich APIs, but since they are storage, uploads and downloads account for much of the requests. This results in a lot of streaming traffic. OBS is a platform that does not know who upload the media into, and it also stores user data securely with excellent security. So I want to talk about the media storage. OBS is located in Japan, Korea, Singapore, Germany, and the United States. So 5 IDCs. This is called point of presence, which is POP. LINE users access the service through a POP that is more geographically close to them. As you all know, LINE started in Japan and now it's loved by global users around the world. So when you use LINE application to share images, videos, or post something on timeline, or put your precious moments in your album, they're all stored in OBS media storage. When looking at LINE news blogs or watching music videos of famous artists and watching LINE live video, we use the contents from that media platform. So as these LINE services grow, OBS traffic has also increased. There's also a lot of data to save. We continue to study ways to ensure consistent incoming and outgoing quality for users and to store them more securely and in a cheap way. So let me talk about the media storage forward deployment project. So I told you that OBS is operating in 5 POPs, but not all components of OBS are deployed in POP. POP operates a large scale of service BO and media cache. So it means that in POP, there's no storage. So let me take a look at the problems and what kind of benefit it has when POP is in a storage. So let's suppose that the recipient reads the LINE media message from the LINE chat. The recipient requests the media sent to them to download to OBS Service BO. Then Service BO checks if the object requested by the recipient exists in the cache. If the object is cached, the cache is sent to the recipient, and the recipient will be able to check the media quickly because they have received the cache results. And it's not written here, but all user requests of LINE include authentication, so it is very safe. But let's say that it doesn't exist in the cache. The cache server takes objects from the storage and caches them to respond to the user. Because the recipient did not receive the cached result, they can check the message at a slower rate than before, but it's still okay. And let me talk a little bit more about cache. Although OBS POP has large cache server, but there are physical limitations. And compared to media storage, cache is a much smaller space. That's why OBS selectively caches objects that will be accessible in the future to make the most efficient use of the cache. For instance, media distributed in group chat or open chat services that may be received by multiple people is worth caching, but the one-on-one chat room will be less valuable to cache than the media in group chat. So as a result, there will be users who will benefit from accelerating object access through the cache, and there will be users who don't benefit from that. And setting up cache accelerating by screening content by OBS may differ in response speed between users. So the first user to request the download will receive the object at the same response rate as it was imported from the storage, because the object will not be cached. And starting with the second user, the first user can use the cached object, so you can enjoy the cache effect. In this configuration, it makes the cache server and the storage server geographically remote. The response speed difference between the cached and non-cached object will be greater. When the media storage itself is forward placed in the country of primary use, the good cases mentioned above are not a big consideration. So there's not much of a time difference. Communications between IDCs in different countries use leased lines. So a leased line, as the term implies, is a line that is leased. So it is very expensive. So instead of paying as much as they used it, it's renting a large enough capacity to accommodate large traffic for events like Christmas and New Year's Eve. And as I said before, POP has only cache without storage. If a cache miss occurs for the object requested by the user, the traffic from storage to import the object will be used in this leased line. This is why cache hit rates are very important for OBS. So the cache hit rate is currently at 70%. Thai users' traffic is housed by OBS Singapore POP. Japan has the largest number of LINE subscribers, but Thai has the largest distribution of media. The production and consumption of images and videos are much higher than in other countries. So 70% of Thai user requests are answered by cache. And even so, 30% of the traffic is still flowing to the storage. The cost will continue to occur. To help you understand the previous slide better, Singapore and Japan were represented by a single line, but in reality, it's composed of mesh like this. And the availability of inter-country line is also different. And as the utilization rate in Thailand continues to increase, the 30% of traffic equivalent to cache miss will also increase. So if so, you will have to increase the traffic availability for each section. And the graphs and availability figures are different than the reality. So it's just an example. If media storage is forward placed in Singapore, any increase in user-facing traffic due to event day or cache miss will be accommodated in Singapore. So there is no significant deviation in the rental usage between Singapore and Japan. In addition to reliable traffic control, Singapore POP traffic eliminates the need to increase the capacity of the leased line contract. So we expect this to lower the maintenance cost. Here's a situation, and it's a rare case. And let's say that there is a OBS POP failure in cache pool. In this case, all requests that do not have access to the cache will be directed to the storage placed in Japan. This results in a surge in the leased line usage, and storage load will explode. So there is a possibility that the users in Japan and Taiwan who use Japanese POP may be affected together by the cache issue of Singapore POP. The graph you see right now is a problem where OBS was updating its cache policy. Singapore's cache hit rate was about 75%, and then it plunged to 15%, and the leased line was close to the maximum contract capacity. Fortunately, there was no outage because the traffic was low. Cache is not just a cache, and it's a necessary component to serve OBS, creating a strong dependency with cache. And this is also another rare case. The submarine cables of the leased line may get cut off. In fact, there were some cases where the leased lines were cut off. In this case, the line repairer will have to go and repair the broken area, and until it is fixed, the service may continue to fail. But when storage is forward placed in Singapore, Service BO detects cache failure and changes them to use storage only. Of course, Japanese POP is not affected by the cache problem in Singapore. In addition, there will be no significant impact on the disconnection of the cutoff. There is another advantage of forward placing media storage to a major line country. For some reason, it is designed to distribute and accommodate traffic by spreading DNS from another active OBS to Singapore POP users in the event of a short period of time that is difficult to resolve, such as network isolation. So OBS plans to operate media storage in at least 3 leases, including Singapore and Japan, so that it can respond flexibly. Since OBS internally manages the re-information of media storage by object, users can upload and download media no matter which POP is in operation by OBS, not specific POP. In addition, OBS may adjust the percentage of storage stored in each of its leases when regional infrastructure situation or line's technical and strategic decisions require different volumes of storage to be operated. Starting with the improved user-facing response speed, reducing infra costs, and securing high availability, the media storage forward placement has a lot of benefits. I'd like to share how we chose our storage solution to proceed its project and how we were able to resolve the technical decisions about the issues that we faced in the project. First, let's look at the basic requirements that must be met as line storage. First is allowing failure, which is fault tolerant. Even if there is a failure, the service must be handled at any time for 365 days in a year. And the second part is consistency. Distributed storage typically creates several replicas of the source to ensure high availability, and you must respond to the same values no matter which replica of IDC you access. Third is resiliency. You need to detect and recover from the problems that occur when moving, replicating, or manipulating data. And the fourth one is scalability. Storage services must be easily scalable without having to be completely shut down. And really, lastly, it is cost-effective efficiency. Minimizing maintenance costs is a must-have part of media storage choices. Today, OBS has deployed storage-saving technologies at the application level and operates the commercial distributed storage there. Because this commercial storage was not suitable for the forward placement in terms of the difficulty of the recruiting professionals overseas and operating costs, it was necessary to find a solution that's suitable for the requirements listed earlier. So we carefully reviewed the open source and we selected Ceph. Ceph was able to get technical support from the cloud storage team because most of the previously listed media storage requirements were met as they were already operating Ceph with linedevday's cloud storage. And thank you so much for helping out the project. So Ceph is available in 3 ways: object, file, and block storage. Object storage is basically a way to save the access and the object key and its corresponding values. Object storage supports Amazon S3 API and has the advantage of being able to utilize the Amazon SDK that has already been implemented. Rados Gateway is a stateless HTTP server that can scale out as much as you want, which is advantageous if you want to expand. And graceful shutdown also enables flexibility in response to maintenance situations such as Ceph version upgrades and patches. And second, you can think of typical file system for file storage. It's also known as Cephfs. The advantage of using this was that POSIX implementations could be used for easy deployment, and Cephfs must have MDS that manages the metadata of the file system on the architecture. Finally, block storage, like its name, is simply a byte sequence that can be used by attaching the device image to VM that requires I/O. Any of the 3 types you've seen before will eventually be stored in a Ceph cluster in a structured way. I was thinking about which way to use it, file storage or object storage. And at the end of many research and POC, we decided to use this one as object storage. And let me tell you about the technical background of this decision. Currently, OBS supports RESTful APIs. Over time, OBS is increasingly required to support the AWS S3 API. Commercial products and other storage products, including Ceph, support the S3 API. OBS also believes that it is important to support the S3 API in the future in order to make it easier to use LINE as media storage. In this project, we will use the S3 API between OBS and Ceph storage and review the support of the S3 API in the future. I mentioned earlier that OBS stands for object storage. In fact, OBS and Ceph object storage have a lot in common. The front end of the storage handles user requests and provides information about data uploaded by the user. So you can store it well in one of the data servers that are set by certain rules referring to a key and value, and you can put multiple replicas to a different data server from the original. So these are common functions of storage, but are different in terms of functions and performance. So the parts that are regarded as better from Ceph can be applied to OBS. And we use OBS media storage uses a mix of 3 types of hardware. The storage shown at the top is good at performance but expensive to configure, but the one at the bottom is relatively low in performance but cheaper, and it can be configured in large capacities. And object access is the most frequent in a few days after upload, and almost no access occurs after a certain period of time, such as a month or a year later. Media storage optimizes both the speed and cost of storage for storage and user requests by moving hardware spec over time to other storage. Although OBS operates this feature as a batch job, Ceph's object storage can create a life cycle rule and set policies to allow objects over a certain period of time to be sent to a specific storage class. The last reason why we chose the object storage is the MDS of CephFS. If an active MDS server fails, standby MDS changes its role to active MDS. The biggest problem with the application of CephFS was the time spent on role change. CephFS blocks all requests until standby rolls to active. According to our experiments, it usually took about 3 to 4 seconds to change the role. It's a virtual single point of failure, and it's hard to accept that LINE MediaStorage cannot process requests for 3 seconds. On the other hand, object storage does not require MDS in architecture, nor does single point of failure exist. We chose to use object storage because a lot of features we needed from CephFS were in experimental state. Next, I will share my concerns on the OBS side when I was working on the project. First, I will explain the background of storage I/O adapter library, and next about object immutability. And lastly, which services will be moved to Ceph. Service BO from OBS has a common set of business logics and platform capabilities to support a variety of line services over the past decade or so. It also included technologies to reduce storage and traffic costs. Finally, there is a layer on which data server on the storage will be stored and I/O will be performed. At OBS, Ceph was chosen for forward placement rather than completely replacing commercial storage, so OBS had to be able to support both storage. Commercial storage used a separate library, and Ceph used the S3 SDK provided by AWS, and there were many different parts that had to be performed. Commercial storage used RCP protocol, and Ceph was using HTTP protocol. And commercial storage library is built in blocking I/O, and S3 SDK uses non-blocking I/O version. Finally, the data flow used to be a push method, but S3 SDK was used. Simply adding the S3 SDK to Service BO was not easy, and we needed to have an improvement in this storage layer, and we couldn't implement this directly to Service BO. Like Service BO, the same thing happened to the image and video processing servers that were doing storage I/O. So with the addition of storage I/O adapters, the combination was lower than previous implementations, and applications were more flexible because they only used abstract storage interfaces regardless of which storage they were using. The adapter was developed based on active streams. And we implemented a publisher that queues user data in chunk units and a subscriber responsible for each storage operation. And because of the nature of the storage of the speed of I/O processing by network environment, we had to call and use back pressure requesting data when it is available to the subscriber. So each storage SDK also benefited from its reliability because each existing implementation could be used without any modification. And the adapter was also built in a library to provide a standardized asynchronous interface for components requiring storage I/O. When you forward a media from LINE chat to a friend, the friend uses copy API from OBS to create a replica. So let's say that if I send it to friend A in A's space, and if you send it to B, it sends it to B's space, and when you pass it to C, it replicates to C's space. But with the addition of Ceph storage here, there's an issue between commercial storage and Ceph. The original may be on commercial storage or on Ceph, but the two storage arrays do not have a compatible API. Again, we borrowed the concept of reactive streams, and we supported copy operations by implementing the publisher of the original storage and the subscriber of the storage to create the replica. And the picture you're looking at right now is an example of an original being on the commercial storage. And publisher on commercial storage queues data by reading it in chunks. And Ceph subscriber consumes this data and writes it to Ceph storage in chunks. Similarly, because back pressure is implemented between the publisher and the subscriber is queuing only the right amount of network speed to handle. So even if there is a difference in network speed between the storage, there is no memory problem. LINE chat has this function, upload function, and let's say that there's a network problem when you're uploading files to your cell phone, and you have probably seen this resend button. This prevents uploading from the beginning to save user packets, and if you click on resend button, you will be able to re-upload, excluding the part that was already uploaded. Commercial storage is file storage, which is the default storage unit for files that can be appended. On the other hand, Ceph's object is immutable, so it cannot be saved if a full upload is not preceded. Ceph supports multi-part PUT. It's a feature that allows you to upload multiple parts and create a complete object. We used this part to support the resumable upload. OBS aggregates packets received from users to a fixed size to create each part and upload them to Ceph. When all packets are received and object creation is required, OBS sends signals to Ceph that the upload is complete, and Ceph creates a complete object by combining the parts that have been uploaded. This is the sequence of multi-part PUT. To use Ceph's multi-part PUT, there is a condition that requires upload ID to be issued, because Ceph can be combined into a single object only for parts that use the same upload ID. So we were wondering if we could improve the RTT overhead of the parts that get the upload ID. We have improved the structure by generating upload ID on OBS and sending it to first part of the multi-part PUT request at once. So as a result, we were able to reduce RTT issued with upload ID. Forward placing data from all services supported by OBS can be cost efficient. So we had to choose which services to use first with forward placement. So first of all, we considered the services that must work in the disaster situation in the service where media storage IDC is located. And next, we reviewed services with limited media retention periods. Migration from existing storage to Ceph is another level of concern and costly, so we decided not to consider it in this project. Finally, we looked at services that take place in areas where media production and consumption are similar, and namely services with high locality as priority. This is because if these services are applied to forward placement storages, it will use less leased lines. After reviewing these conditions, we were able to conclude that the messaging service was the best suited case for the first project. So finally, we will share the future challenges of storage forward placement. So storage forward placement has been serving open chat media since last October. Next year, LINE message service will also apply this. We are also considering deploying additional media storage to the major hub countries. We will also continue to select which services will be added with storage forward placement. And the following is the enhancement of OBS's APIs and protocols. Open source storage and commercial storage supports S3 API of AWS. So even if you don't understand the internal structure, the Open S3 SDK allows unified API users to use the storage. OBS is also reviewing S3 support for users. While OBS has supported protocols such as SPDY and HTTP2, we continue to study more efficient protocols specialized in media transmission. This is the end of the presentation, and thank you so much for watching.